Hello everyone and welcome to the latest MDPI webinar on geosciences entitled State of the Art and Future Interdisciplinary Challenges. This is the first webinar of a series based on special issues and sections from our Geosciences journal. This webinar is chaired by Professor Jesús Martínez-Frías from the University Complutense Madrid, Spain. Professor Martínez-Frías is currently scientific researcher at the Geosciences Institute, honorific professor at the Bioengineering and Aerospace Engineering Department of the University Carlos III of Madrid, head of the research group of meteorites and planetary geosciences, and founder and director of the Spanish Planetology and Astrobiology Network. He has participated in NASA and ESA missions and in more than 40 projects spanning the globe. Thank you, Jesús, for accepting to chair this webinar. I would quickly like to remind everyone that this webinar is recorded. The recording will be made available as soon as possible and will be posted on the webinar's webpage. If you are interested in submitting your paper to a special issue related to this topic, it's available on the webinar's webpage. And today there will be three presentations given by Dr. Suppasri, Professor Bielecka and Dr. Cortes. These will be followed by a discussion and a Q&A session moderated by Professor Martínez-Frías. If you have any questions, please feel free to post them in the Q&A box, and our speakers have kindly accepted to answer all unanswered questions in written form. These will be available alongside the recording. And now, Jesús, the floor is yours. Enjoy the webinar.
Thank you very much, Charlotte, for this introduction. It is a great pleasure for me to introduce the three speakers of today. The first speaker is Dr. Anawat Suppasri. He completed his bachelor degree in civil engineering from Chulalongkorn University in 2005 and a master degree in water resource engineering from Asian Institute of Technology in 2007. He went to Japan and obtained the PhD in tsunami engineering from Tohoku University in 2010. And after that, he received research grants to continue his research of tsunami risk assessment in the Tohoku University. After that, Tohoku University established the International Research Institute of Disaster Science in April 2012, and he became associate professor at IRITS since then. After the 2011 Tohoku tsunami, he took many of visitors and professors from both Japan and overseas to tsunami-affected areas. At present, his research focuses on tsunami numerical simulation, tsunami fragility analysis, tsunami warning, tsunami evacuation, and disaster mitigation education. I think it is important to note that with regards to geoscience, Professor Suppasri is the guest editor of the special issue about interdisciplinary geoscience perspectives of tsunami, the volume 3. So, thank you, Professor Suppasri. The second speaker is Professor Elzbieta Bielecka. She is a full professor at the Faculty of Civil Engineering and Geodesy at the Military University of Technology in Warsaw, where she heads the group on Geographic Information Systems and Science. She holds a graduate degree in Geodesy and Cartography and a PhD in Geography from Warsaw University in Poland. She has nearly 40 years of experience in education, research, and consulting in the field of GIS and cartography. In her research, she focuses on the theoretical issues of GIS, especially data quality and uncertainty, spatial modeling, land cover, land use models, spatial pattern analysis, etc. She is also the author of many research publications, consultant in the implementation of GIS in public administration, and she was a member of TWG Inspire for Land Cover TEM. Currently, she is editor-in-chief of the Geodesy and Cartography, the journal of the Polish Academy of Sciences. In connection with our journal, with Geosciences, Professor Bielecka is the guest editor, together with Dr. Malgorzata Luke with the title, A Geospatial Analysis Model for Land Use Change. And finally, our third speaker is Dr. Joaquín Cortes. Dr. Cortes is an igneous petrologist with experience in geochemistry, volcanology, and structural geology. He completed in 1994 his Bachelor in Science in the University of Chile, obtained the professional qualification as a geologist and his Master in Science in Geology in 1996, and his PhD in Earth Sciences from the University of Leeds in 2005. Since 2006, he has been lecturer in those subjects in the USA, in the University of Buffalo, and in the UK, in the Edinburgh University, Newcastle University. Dr. Joaquín Cortes is currently a senior lecturer in geology at Edge Hill University in UK. And also with regards to our journal, to Geosciences, Dr. Cortes is the guest editor of the special volume about thermodynamics and kinetics of magmatic systems. So my special acknowledgement, my special thanks to the three speakers. And Professor Anawat Suppasri, you have the floor.
Okay, thank you for your introduction. So let me share my screen. Okay, great. Yeah, so thank you once again, MDPI, for this opportunity. Actually, I've been working with you guys since a few years ago. This is, as the introduction, I have a special issue. This is the third one. So yeah, I've been working with them for a couple of years. And yeah, for some conference in the booth or some exhibition. And I heard that you also have the a new branch in Japan, in Tokyo, isn't it? So I hope we can, my office in Japan, so we could have extend more our collaboration in the future. My title for today will be about tsunami, but as you may have known that most of the tsunami source are the earthquake-generated tsunamis, which is like 80–90% of tsunami in the world. But yeah, like 2011 or in Japan, or 2004 Indian Ocean, Indonesia, or other Indonesian countries. But as I mentioned here in my title, the silent tsunami, because recently, actually in Indonesia, there were two tsunamis that actually generated by landslides and volcanic eruption. As you might know that in Japan or other countries in the world, we have the global network of tsunami observation, real-time detections. So we can, or even local for each country, we can detect if the earthquake happens, then we have some database pre-calculate tsunami from the earthquake, assume tsunami, earthquake scenarios or parameters. So we use this kind of database for the earthquake generated tsunami warning. But this kind of non-seismic events, it was very difficult for even in Japan, if it happened, to make a warning. So today I would like to share you some of the lessons from these two unfrequent, very rare tsunami, but still very important in our tsunami communities. And actually my background is civil engineering, so I'm also interested in the interaction between the tsunami and the like people or building, something like that. So at the end of my presentation, I want to show how we related the tsunami force and the damage to the building, something like that. All right, so the first one is about the one in Sulawesi Island in Indonesia. You can see where the island is. It is in the northeast of Indonesia. Here, Sulawesi Island, and the capital city of this island is called Palu. And at that time, the earthquake was 7.4 something. And well, in terms of the magnitude, it's not that small, not that big, but enough to generate tsunami. But the thing is the mechanism of the earthquake, because normally the earthquake that can cause tsunami will be like we call strikes like vertical change of the fault. So that like 2004, 2011, it's called like that. So dip slip. So but this time it was strike slip, so the fault moved laterally. So even though the magnitude is not that small, but because of the fault actually moved horizontally. So at the time, the scientists or the government in charge of this, they didn't think about the big tsunami that would be generated in this area. And actually, in this bay, there's one tidal station that could record the sea level change, the water level. But because of the earthquake, that stopped the electricity, so the main warning center in Jakarta could not receive the wave signal, the actual the real-time observation. So what happened? So after the earthquake, 5 minutes, there was no power, and there was a warning, but later it was canceled because they could not observe the waves, and also because of the lateral movement of the fall, they thought that there will be no tsunami. So then, yeah, but after that, from SNS Twitter or something like that, there was a very news report about tsunami attack, very big tsunami, and killed many people in this bay. So there was a big issue after that. So there are several reasons for that, why even the earthquake generate horizontally movement of the fault, but why still have tsunami. Actually, for example, the first reason, like if you have very high slope like this in the ocean, and even it moves laterally, you still have some component of vertical movement that can still generate tsunami, or like liquefaction that can make the slope failure, like they can see here from the loose of the land here. But for us, another big reason is that, like, when you have the soft sediment from the river flow from the upstream to the downstream and deposit in the river mouth. Yes, so imagine that we have very soft sediment like this. Can you see my cursor like this right now? Okay, so yeah, so this is like a soft sediment. So even so after the earthquake, it can shake, and this sediment will move as a landslide, and then it generates tsunami. And we have some observation from the airplane that luckily, not luckily, but I mean at that time, just the airplane flew over the bay, and from the video, it could record the numbers of, you can see the white spots, the one, this one, or this one and this one. There are several wave spots that could taken by the video from the sky, and we could confirm that this earthquake and landslide could generate the several local tsunamis. So to answer this question, we apply our in-house numerical simulation of tsunami, and we have assumed the source of several landslide inside the bay, like in this area, the L and the S locations. So in our model, we model the soil and water interaction, and the movement of the soil will be the generation of the tsunami. So you can see here, for example, there are several tsunami that were generated inside the bay, and because this is the time, so you can see again, sorry. So this is 2 minutes. So 3, 4, 5. So very soon, within like 4 or 5 minutes, the tsunami already arrived. So it's very difficult to warn people within 5 minutes after this kind of phenomena. And there are some issues about the landslide, the topography data, because at the beginning we got the digital surface model, so we have to remove the height of the building like this. And we also have, as I mentioned at the beginning, we have the one tidal station that could observe the sea level change, but just because of the losing of power, because of the ground shaking, but they could recover the waveform, which is the time series of the water elevation at each time later. So these figures show the comparison of our model simulation and the observation. So the figure here shows if we only model the tsunami from the earthquake, like in this one, you can see that the orange one is the simulate one, and the blue one is the observation. So you can see that only the earthquake source cannot explain the size of the tsunami, but if we include the landslide source, we can much better explain the size and the period of the wave in the bay. And we also have the inland observation. So yeah, this is how we verify our simulation accuracy. And the simulate flood area in the downtown of Palu also we have a good agreement with the observe the flood area as well. And there are some bathymetric survey after the earthquake. We can see that some cross section like this. This is a proof that there are some sediment that move from somewhere up and deposit here as the source of the tsunami as well. So by compiling the simulated tsunami data and the damage of the building data, actually my interest is like to understand the relationship between the tsunami and the damage of the building, so we can fit using some statistical approach, so we can correlate the data like this. So you can see here in this case, when the flow depth is about 2 meters, the damage probability of the building is like 60%. So by knowing this kind of information, if the tsunami happened in the future in other areas, so if we have simulate hazard map or the flood depths, we can estimate the damage of the building in the future. So second is about the Sunda Strait tsunami, also in Indonesia. It is in between the Sumatra Island and Java Island, and we have Anak Krakatau, which is the volcano right in the middle of the Sunda Strait. There are some seismic waves from we can observe the seismic record from the eruption, and from the satellite image we can also see that the volcano before and after, where the topography or the losing of the land before and after. This time the eruption was happened like, I don't know how to explain, but the on the side of the volcano, and because of the explosion happens here, and then the slope lose the stability and then cause the landslide and then generate tsunami. So this kind of phenomena is very difficult to predict, right? And we have there was no any sea observation sensors around the volcano at that time. So and also because this is not earthquake, so there was no tsunami warning at that time. So just suddenly the wave hit the shore and killed the people. So there were several field survey, and like the height of the tsunami, or we can see the border that was transported by the tsunami, or like the satellite image before and after the tsunami. You can see that with the large tsunami could destroy all the vegetations, or for the places that the vegetation is still available, it can save the house behind. But the place where the wave was large enough that washed away all the vegetation of the trees, all the house also got damaged as well. So from the field survey with my colleagues, they measure for example, at each building, they measure in case of tsunami, there's a mud that still, remains on the wall. So we can measure the flow depths from the marks, the mud mark on the wall and the ground. So we can measure the flow depths, and we can evaluate the damage, building damage scale level, something like that. For the simulation itself, as I mentioned, from the comparison between the topography data and the satellite image before and after, we can calculate or estimate the volume, the losing volume, the volume that minus loss. So we can estimate the volume, and we assume the duration of the slide. Then we can apply this estimate volume and sliding time in our tsunami model. And for example, this is how it looks like. You can see that something like this, the slope valley here, and then generate the tsunami throughout the Sunda Strait to both Sumatra and Java side. And yeah, so we have also calibrated our model with the observed tsunami waveforms, and you can see that we have some reliable agreement between the simulate waveform and also the tsunami height along the shore. And this is just how we verify our simulate tsunami height and also survey tsunami height. And yeah, from the field survey, we could measure the tsunami flow depth and the damage of the building. So we can also plot the curve for different types of damage level against the damage ratio. For example, this time, if the water flow depth is 4 meters, in this case, it is about 40% chance of the building will be damaged, will be destroyed. So this is my last slide. So so today I present two tsunamis. The one in Palu, the first half, it was earthquake and then large liquefaction and then tsunami with short period. But later in the second half, there was no shake, so the building only suffered from a short wave period. So I would like to compare the building damage characteristic of these two tsunamis and another tsunami in 2004, Indian Ocean tsunami, because that is another tsunami in Indonesia. So they have similar building types, construction types. So as you can see here, in 2004 Indian Ocean tsunami in Banda Aceh, with the 2-meter flow of tsunami, only 20% of damage to the building. But in case of Palu or Sulawesi island, because it is not only tsunami, but very strong liquefaction that reduced the performance of the building and caused some damage to the building before tsunami arrived. That's why at the same flow depth, the damage of the building is higher than in case of no liquefaction. Or if we compare this one on the right figure, Indian Ocean tsunami and the Sunda Strait tsunami, you can see that for Sunda Strait tsunami, because Sunda Strait tsunami was generated by the landslide tsunami, which is the point source. So the wave period is short. But in case of the earthquake tsunami, the fall of the earthquake is like 100 kilometers or 200 kilometers. So the wave period is very long. So that means the time once the wave train hit the buildings, it's sustained longer period than the short period. So we expected that even, for example, the same flow depths, for shorter or for longer wave period, the damage probability of the building is higher. So again, to summary, so I have shown you how the very not low frequency tsunami types and how hard the warning is, and from the interdisciplinary, we integrated the geoscience, which is the earthquake and tsunami geoscience perspective, and we apply engineering simulation and also the civil engineering perspective of interaction between the tsunami and the damage assessment. So yeah, this is the end of my slide. Thank you very much for your attention. Because this is the evening time in Japan, so I have to leave after this. So I will take 5 minutes maybe for if you have any urgent questions, or after that, I will be very happy if you to answer your question by emails. Thank you.
So again, thank you very much, Dr. Suppasri, for your excellent presentation. And I hope we continue in contact in geoscience. And it has been a great pleasure to have you here with us in this webinar. So thank you very much. And I'm going to give the floor to the second speaker, Professor Elzbieta Bielecka. So Professor Bielecka, are you ready?
Yes, I'm ready. I just share my presentation. So good morning to everyone. Thank you for introducing me to the broader audience. I was asked to prepare a presentation about land use change models, but not all of them, because it will be too broad team, but only those that are explicitly spatially oriented, so we can say that they are GIS-based or GIS-oriented models. As we know that land use change represents the interface between biophysical condition of land, always called as land cover, and anthropogenic influence throughout the time. So generally, these two concepts, land use and land cover, are combined, and we can find land use, land cover change models, or sometimes they are also used interchangeably. What is worth to remember that changes in land use always occur in multiple geographical locations, generally locally. Sometimes it is very small area, sometimes it is quite big, like in the tropical forest in Amazonia, but anyhow, it is always locally. But the local changes influence also changes in some distant region. For example, if one country introduces some forest protection law, it results in growing timber imports from other location, and in fact, deforestation in some quite distant regions. So we have to remember that everything that we do in land locally have global influence, and finally influence climate, and climate in a direct way influence also land use. We can see here some flows. Researchers generally mention that population growth and connected with it rising competition for land is the main and the biggest driving force of any changes in land use, because we demand more and better food. We want to live in a better condition. So it resulted in rapid urbanization, agriculture intensification, deforestation. So in turn, provides to biodiversity loss, greenhouse emission, impact on carbon cycle, climate change, and we can start from the beginning from food demand, because when there are severe climate events like floods, tsunami, and so on, the agriculture area is inundated, so we need more food in different places and so on. When we are talking about land use change modeling, we have taken into consideration three aspects. First, of course, is the data from at least 2 periods. The second is a theoretical background, which allows us to elaborate some tools, and tools in turn are necessary to run this modeling and to assess how big the changes are. There are, of course, plenty of different models and theories, but generally it's not only my opinion, but many scientists, that the first law of geography set up by Toblers in 19th is very, very important. The law said that everything is related to anything else, but near things are more related than the distant things. And in such a way works interpolation, geostatistics, and many, many other tools which we have implemented in our software packages. But of course, we have to remember that our area of investigation is not an isolated island. So the second Tobler's law of geography said that everything what is outside our area of interest also affects what goes on inside. And there are probably 2 more, but very general laws that are implemented in plenty of tools. Of course, when we are looking less from geographical, but more from socioeconomic point of view, it is also Dunant's model of agricultural land use value, which has a form of a concentrated circle, and the agriculture good changes its value depending on the distance from central business district, in fact, the central market. Academic community is interested in land use modeling since 70, generally also using this some kind of GIS tools. And at the end of May, I checked Web of Science database, just looking for land use change modeling publication, and found almost 44,000 different kind of publication dealing with land use change modeling, and among them more than 3,500 those that use the explicitly special oriented modeling. You can see on the chart that the number of publication is growing very fast, but also what is very important, the citation is also growing very fast. So what does it mean? That there are a lot of readers who state that this publication, the finding by authors, are very important, and they cite them and use them in their publication. When we can use, when we can look for the keywords from this 350 publication, we can see some groups, and that group, those groups reflect the research interested in different aspects of land use change. The red one is generally devoted how land use change influence soil erosion, soil runoff, or soil pollution, and water. So we have seen here river basin, water pollution, watershed, and so on. The second, the blue one, the complex study, which researchers try to estimate how land use change affects global landscape, ecology, biodiversity, sustainability. So you can see also here this very relate connection about land use and land cover, because here is an also big circle showing land cover. The third group, their study connected with urbanization on one hand, but on the other hand, on some tools that are used to get information how urban area expand, or how we can predict this, expansion. So you can see here just some statistical methods like Markov chain or logistic regression, but also cellular automata, intelligence, artificial intelligence. But when you see also very big circle about simulation, because those models are generally very advanced and not only simulate the two results, but also give, or maybe you can see here, different scenarios. So the policymakers, the scientists have on the plane some different scenarios which inform us what could be in the future if something is happened now or happened years ago. So when we try to summarize what are still very important research topics, so we can say that the answer on the question how changes at the local level affect the global changes is still unanswered. And a lot of researchers try to solve the problem, but so far I didn't have those that state, okay, it is already everything known. The second very important problem is uncertainty in land use modeling. Because we have data of course has some level of inaccuracy, and we have the results, and even if we validate the model, there's also some margin of uncertainty that is important to any decision maker. And of course, a very new, very important trend that said that existing models, existing tools need to be refined, because now we, during to the globality and during to the interdisciplinary approaches and a lot of drivers from different science disciplines which affect land use should be taken into account. So a lot of research papers are devoted to develop some new approach for land use change modeling. A few words about uncertainty, just to imagine what the problem is. This is, the picture presents the differences in extent of one land cover element, forest. The data are from MODIS, from GLC Global Land Cover 2000, and from other European-based land cover databases. Generally, all data are derived based on satellite images and automatic classification, but the extent of forest differs significantly. So it is easy to imagine what happens if we use one data set as a past data set and the second data set as a training data set, and the results, of course, will be not the same. And the second problem, I think more complicated to manage, is semantic heterogeneity. In fact, we do not know if the data set, which were data on land use or land cover, which were derived, for example, on topographic maps. And now we have a data derived by automatic classification on very high satellite images. If the forest, understanding of what is the forest is the same. Because in general, there is no description very detailed, especially to the very old data set. And many researchers try to solve the problem, of course, not by unification, because it is not possible, but some kind of standardization, of harmonization, how we can move from one land cover classification system to the second without losing any important information. And here very promising are different approach to ontology-based semantics. When we, when we analyze the literature, we can see that there are at least 3 types of model. The descriptive, which generally is geographically oriented, typical GIS model, because they show the pattern of changes and using some pattern, special pattern analysis, data mining, sometimes regression or exploratory data analysis, and show in qualitative and quantitative way the changes. The second group are predictive models, so some forecasting, and if they are only data statistical, they are based on socioeconomic mainly aspects, but even if we use only statistical data, we have to remember that it is always spatial context, but maybe not geographically explicit, but we thought about some regions, some country, which we know where is located in the space, but it is indirect location. And the more promising, more complex system models, prescriptive, based generally on hybrid approach, maybe artificial intelligence, machine learning, some kind of regression, because at each step of the modeling, we need to use different tools. For example, for weighting the factors, regression is very good, or Markov change, and then machine learning and cellular automata to showing the exact location of changes. And we have already a lot of models already in play. Some of them are oriented only on one change, like the first one, which is typically urban oriented, or some have a broad context like the CLUE model that could be used for landscape, deforestation, urbanization. Some of them are typical based on socioeconomic theory, like LOV gravity model or PLM. The Moland is a very old model prepared in the frame of a joint research center. In fact, I am not sure if it is still available, but sometimes it was very, very popular, especially in Europe. And of course, some of the models are semi-clone, some are implemented in our GIS software, especially Idrisi and also ArcGIS, but maybe also in others. And just look for one publication. The publication was chosen because it was, it is very high cited, prepared from researched from European countries, and deals with land use change modeling with cellular automata and artificial network on the cross border of many countries. This is an area of investigation. You can see that this is part of Belgium, Luxembourg, France, and Germany. And some results and preliminary assumptions. So we can see that the model implement a huge amount of variables that I grouped in seven types: connected slope, transport networks, water, and many others, and some workflow, how the model is run. In fact, this model has a form of a different kind of algorithm combined together, and the results. This is the map which was simulated, so we can compare the result with the map made. I think that this is Corinne that covers a map on visual interpretation of satellite images. And here are simulation as the result of running these models. Of course, it is very difficult to find the difference, but look here. Here is a prediction of big urbanization, but in fact, it haven't taken place. And the final map showing the places where the differences were easily visible in the observed land use and in simulated. And finally, some metrics showing the accuracy. The results are really promising because the overall accuracy made by kappa coefficient is nearly 89%, but of course you can see that the urban accuracy is not maybe so high, but anyhow the results in comparison to other models are really very satisfying. And when we go to this special issue, it is very important to articulate the key role of human impact on the environmental changes, among other, the biodiversity, the climate, which is caused by land use change, including the driving forces, showing the geographical location of very high or very low rate of land use changes, and just to describe some trajectories of these changes. The second, it is very important to inform not only academic community, but I think that all public, local authorities, policies, and even common people about the value of monitoring land use and human impact on the earth sources. And this is very connected with the special development goals, which just now is a very hot topic in any kind of research. And finally, it is also very important to describe the benefits of using GIS technology and geoscience in theory and land use modeling. And I don't know if I have time, but maybe a few conclusion that I think that we all know that there is no universal models or universal techniques, and the model and the technique we use or computational approach is tailor-based to the local location. So thank you for your attention, and I'm ready to answer the question at the end of the seminar.
Thank you very much, Professor Bielecka, for your very detailed and excellent presentation. There are many different aspects which have been covered, even about semantic. So I think it's a multidisciplinary approach, and thank you again. There are no questions, so thank you again, Professor Bielecka. And as I told to our former speaker, I hope we'll be in contact for the future. And now I'm going to introduce the Dr. Joaquín Cortes, Professor Joaquín Cortes. Thank you for being here. And please, the floor is yours.
Okay. Right, thank you for inviting me. I am a volcanologist, so I'm going to talk about things that are rather different than the previous speaker, but I hope I could introduce you with the topic, and if you're not a volcanologist, well, I hope some of the key messages stick with you anyways. The first thing I'm going to show you is a rather low quality, really basic picture that I took from the internet of a model of a volcano. And the reason why I choose this one is because most of the people, even old-fashioned volcanology, even people who work in the subject, say 20 years ago, had this imagine of this cone, the magma chamber there, like essentially a container, and then magma pumping in from below, and then the magma goes up outside. The first thing I want to talk about is the fact that this model, very simplistic, is no longer what we think about magma chambers. We have moved away from this, and currently we have a really more complicated idea based mostly in geophysics and some of the work that people like me, petrologists, have done checking the volcanic product. Essentially, we no longer believe in a chamber, in a room, essentially, where magma is stored. Rather than that, we believe it in pockets of something that we call mash nowadays, because it's not really liquid. It's a mixture between solid bits, crystals, and molten material. So in terms of structural properties, it behaves more like a mash, which could be activated by the arrival of new magma. So the picture at the right is from a geophysicist researcher who did this conceptual model, and the idea is to have what we call the crystal mash, the transcrustal volcanic system, in which you get an interconnected network of areas that don't quite behave like liquid, don't quite behave like solid, but they could change behavior with the arrival of new magma. And what is interesting here is that new magma arrives in a form of a dike, which is essentially the injection of new material from below whatever is below, into the transcrustal system. So all these pockets of magma are interconnected, might not be, and then when a new dike arrives with new magma, might actually hit essentially this pocket of magma, or might not, and might come out elsewhere in the volcanic system. Some of them actually make it to the surface, and then you get what we call a lateral eruption. Sometimes these guys hit into a pocket of match, activating it, and then you have a central eruption in the volcano. Right, so having said that, I have to talk a little bit for the purpose of the rest about how dikes propagate. And essentially the idea is you have a stress field, so essentially how the forces are spread in 3D. You get an orientation where you have maximum stress, an orientation you have minimum stress. And the idea is that dikes propagate, oops, wrong, propagate actually perpendicular to the orientation of least compressive stress. This is simply because they have to open space to actually being able to inject in itself. That has huge implications, obviously, because if you have, for example, a volcanic edifice, a cone on top of a volcano, then you've got the load of the volcanic edifice being the maximum stress. But the magma chamber model could still be used to explain all this network of pockets of magma. Essentially, you have an area in which you have much, an area where you don't have much, that would affect essentially what they are going to do. And if you model it with higher density of much versus lower density of much, and this much is over pressure, then the most likely scenario is that the dikes are going to be deflected towards this center, simply because the maximum stress is not going to be vertical. They're going to be affected by the overpressure that the different pockets of magma have. And then you can see this in experimentally, if being done. One of my former students, Pansino, working in New Zealand, essentially with an analog model, simulate essentially an overpressure region, and then injecting into gelatin, basically some other fluid. He showed that it is the case. The actual stress field can be modified by the pocket of magma or by the volcanic edifice altogether. In fact, if you look for older eroded volcanic system, which you can see below, you can see the plumbing system, then you see that that's quite often the case. So for example, here I have two images from the States, so Summer Coon in Colorado, or the very famous Chip Rock in New Mexico, in which the whole volcanic edifice is being eroded, and then in the picture to the right, you can see how the dikes are actually pointing toward the central area with a higher density. In the lower picture, this is a map of one of my former students. Essentially, all the dike system, all the recharge, we call them, all the new magma arriving into this region with much actually get deflected somehow into a central edifice. So that is to give you the content we're going to be talking about, because I am interested to know what happens when you have other big factors that might affect the actual local forces, the local stress. What about if you have big faults or other reasons that could affect the system? And essentially, this is a work that's been done in the last 20, more than that, in fact, oops, in Chile. Just to give you an idea, the left map there show you essentially the location of the volcanic arc in the southern volcanic zone of the Andes. There is a subduction zone, so essentially you get melt being produced in a mantle wedge, and that comes up and essentially have to deal with the grass that have this transcrustal system. So to add more spice to this model, particularly this area has a massive megafault that goes for about 2,000 kilometers in parallel to the subduction. We call it the Ligini-Ofke fault. It's rather complicated. It has duplexes, have a lot of branches, like, you know, all big faults like San Andreas or something like that. I'm going to concentrate in, well, if you look at the right picture, essentially the two branches of the fault that split above the 41 latitude south. And I'm going to look at three volcanoes which are located in different geometries in relation to the fault. So I'm going to start with Villarrica volcano. I don't know if you guys can see my pointer. So essentially Villarrica volcano is right on one of the branches of the Ligini-Ofke fault. Then I'm going to look at Jaima volcano, which is more or less in a similar geometry than Villarrica, but slightly more offset. And then I'm going to look at Quitrupiyan volcano, which is right in the middle of a block between the two branches of the fault. And the idea is, well, the assumption is that all these volcanoes, in terms of the subduction, in terms of the big picture, get the same source of magma from the mantle, but they behave differently simply because they're being affected by the geometry articulated by the tectonics, essentially. Right, so Villarrica, Jaima, and Quitrupiyan. I'm going to start with Villarrica because this is going to be my baseline. I'm going to assume, well, first of all, these pictures show you from above how this guy look like. Villarrica is the one closer to you, to the screen. Quitrupiyan is the rather eroded system behind. The volcano further down towards Argentina is called La Nina, and I'm not going to talk about that one, but it's active too. But essentially, to make my point, Villarrica, Jaima further north, and Quitrupiyan. So Villarrica volcano is one of the most active volcanoes in Chile. Have erupted about 500 times in the last 500 years. So essentially, every year has a bit of activity that you can see. You could actually hire a tour, and they can take you to the rim there and see how it's churning, how things are coming out. It's always active. Every 5-10 years has a kind of major explosive event. We call it violent strombolian, that kind of activity. And essentially, the important thing of Villarrica is the fact that it seems to be doing the right thing. Essentially, the magma comes and is basically diverted to the surface relatively efficiently. Incidentally, this is how it looks from above. If you look to the left of this picture, you're going to see a little line of ants. They are walking toward the rim. Well, those are the tourists going to see the activity. Villarrica has a lava lake, so the actual system is open to the surface, so you can see all the time basically bubbling all the magma on the top. So it cannot be more efficient, the transport of magma from where it's produced in the mantle all the way to the surface. When you analyze, I'm sorry if you don't quite understand the graph. If you don't, well, the take point of the story here is this cluster of blue analysis being very, very localized in an area, or any of the blue symbols here represent the current activity. My point with this mineral chemistry here, the composition of the mineral, or the whole rock chemistry, is to show that that magma doesn't have any variation. It's the same all the time, coming out with the same composition, always with the crystals of mineral like olivine and clinopyroxene, more or less with the same composition. So essentially, there is no major effect of the big structure simply because Villarrica is in an open tensional regime. So what happens if you are in a slightly different geometry? What happens if you are not quite in an open system? That would be my next volcano. It's called Jaima. Jaima is relatively close to Villarrica, about 30, 40 kilometers to the north, but slightly offset in relation to the fault. So here, the different domains, compressive domain versus tensional domains, have slightly more influence in the volcano. And for sure, when you look it from above, the fault is here to the right. I don't know if you can see it, but it's very clear that topography changed drastically if you move further to the east. And then when you look at close-up of the volcano, you're going to notice that there are a lot of little, let's call it spots that are not quite on close to the volcano. So essentially, my point earlier, in this case, some of those dikes are deflected toward the major density of match, and then you get a central volcanic eruption, but some of them are being affected by the regional tectonic, essentially the fault, and the interplay of the fault with the subduction, and they don't hit essentially that match zone, and they get deflected, and then they come out in different places, like you see here at the north. And that's the geological map, and all these red dots that you see there are essentially eruption that came out in different places of the volcano, not from the central edifice, which is indicated here with a couple of stars. Jaima, by the way, have two vents. And just to remind us that this is where more or less is located in relation to this mega fault. Right, so when you look at the products, at what is coming out from the volcanoes, essentially you're gonna notice something really, really interesting. Oh, well, I am a petrologist, I got very excited about these things. The product of different cones are different. And essentially you get, in the main volcanic edifice, lot of crystals of this main mineral, olivine, clinopyroxene, the same chemistry than Villarrica, the previous volcano, but then some of the products are different. They don't contain the olivine and the pyroxene like the central edifice or some of the cones. So you have two populations of cones, one which erupt something very similar to the central edifice, and another population of cone that doesn't seem to be erupting the same magma. So what's going on here? In the old time, all petrology would say, well, we have two different magmas coming. In fact, it's not the case. What is going on here? Okay, again, this is the composition. So in this diagram, you can see that we have variability. We don't have only one type of magma. We have something that is spread in a bigger range. It's the same with the composition of the minerals. All this diagram to the right is just to show you mineral chemistry, we call it, so the composition of the mineral. And the takeaway home here message is that you have a huge spread in compositions. In fact, if you take the magma that comes from the central edifice and compare with the other, you could actually model that changing composition by processes that we call fractional crystallizations and evolution. So what we found in the volcano is those cones that are different, in fact, share similar characteristics with the original magmas, but they have evolved. They have made crystals that have been removed later on, thus changing the composition of the final magma. And if you put this together in a model, you're going to see that in the picture here, the cones or features essentially that are oriented, how is this, northeast, southwest, in blue, the blue lines in the pictures are the ones that are more evolved. And the ones that are shown in red here are the ones that behave like the central edifice. If you put a tectonic model here on top of that, you're going to realize that the orientation matters, because due to the tectonic of the fault, the whole area has an SC kinematic deformation. Therefore, there are areas in which you have more compressive stress and areas that are more tensile. And the assumption here is, obviously, if it's more compressive, it's more difficult for the dike to actually go. Therefore, having time to cool down and essentially evolve. While areas in which you have a more tensile situation, which is the whole point in Villarrica, then magma comes out unimpeded by the compressive tectonics. And that is really important because it means that not pockets of magma are the same. You get a lot of heterogeneities in the system, and dikes that come with different compositions, with the original composition the same, but evolving depending on the orientation in which they are propagating, and those would erupt different composition, even though the original magma is the same. Right, last but not the least, Quetrupillán volcano. So again, just to remind you here, Quetrupillán is in a block that is mostly compressive because it's in between two branches of the main Lignyovsky fault. This is what is currently a current ongoing in process with one of my students. And essentially, it's really, really close to Villarrica. So the expectation is magma should be very, very similar to the Villarrica magmas. In fact, it's not the case. But anyways, when you look at this and you map it, again, Quetrupillán has cones, and all around Quetrupillán you get fissures oriented in different orientations. So you would expect, again, some variation in the tectonic. But on top of that, you have all this compressive regime that essentially would have a dramatic effect in the final volcanic product. So the surprise is when you look at this magma, when you check them out, oh, the legend already spoiled my surprise. But anyways, what you get are really, really evolved magmas. You get what we call trachytes, essentially alkali-rich andesite, intermediate magma. You get trachyandesites, trachyte, which are really more like dacite, and basaltic andesite, which is what you would expect because it's what Villarrica erupts unimpeded, essentially. Again, I'm going to show you all the chemistry, and then the diagram show you where Villarrica is in blue and where Quetrupillán is in red, essentially. So a lot of variation in the composition, a lot of changes. If you look at the mineral chemistry right to the left, then you get not much variation in the pyroxene, but quite a bit of variation depending on the different magma that is coming out in the plagioclase or in the oxide and the spinels. Again, you could do all this modeling, and again, you would find that you could essentially add in the crystal that has been removed to the trachyte the basaltic andesite. So if you take the trachyte, you take the basaltic andesite, you mix them together in a proportion, you add some crystal here and there, you end with the trachyandesite. So the interesting thing is magmas are changing by this process of evolving to compressive stresses, but also they interact each other in the crystal mesh. So that's quite cool. More important than that, it gives an insight of this transcrustal model where you have different pockets of magma with different composition and how they interact each other. Yeah, the next slide to show you that we could model all these things in really easy way, and then you get adding certain amount of crystal or certain composition, then you get basically what you would expect. So if you measure the features, you're gonna notice that they are oriented in different ways, and if you put again a model on top of this, then things behave differently if they are in a compressive regime or in an tensional regime. I have to add something else. The basaltic andesite, basalts, it should produce an andesite, so there is an additional ingredient into the cooking here. The diagram to the right show how the different chemistry of trace element behave in Quechupeyan and behave at Villarrica as well. And Villarrica is the blue one. And you see Villarricas tend to be flattish to the right of the diagram, suggesting that what is coming out is pretty much the original composition from the mantle, while Quechupeyan tend to be enriched in certain elements that are more associated with the crust. So the additional ingredient, obviously associated with the compressive regime, is the host rock. If you have a compressive regime, dike have to work hard to actually propagate. So they have the fractionation, they evolve, but also they interact more with the country rock, becoming what we call contaminated. Right, so to put a model, again, those are the two branches of the fault, and if you take into account everything that is being mapped, essentially there is an orientation in which you have compressive, and an orientation in which you get tensional. When you get tensional, surprise, surprise, basaltic andesite come out. When you get compressive, something more evolved, even with crustal contamination in the case of Quechupeyan, because here the role of the fault is very important. So the compressive regime is at its most. So essentially the magma not just fractionate like in Jaima, also interact deeply with the crust. To finalize, magma chambers are not chambers. They are pocket of interconnected network of what we call mesh. So it's something that is mostly crystal combined with liquid in a kind of transient state, which they can be activated and become low viscosity and is actually runny by the injection of a new dike. The stress field, it's really important for the composition of the magma. Sadly, that complicates our life as volcanologists, because now the simple model of magma coming in, magma coming out doesn't work. So you have an intrusion, a new dike coming, cutting through, might or might not erupt. So that's what I wanted to say, and thank you for having me today.
Okay, thank you very much, Professor Cortes, for your very clear presentation. Also merging different aspects about the geological context, the petrology, the geochemistry, the faults, and also some clarifications about the magma chambers. I think is very good presentation. Thank you very much. So now we have time for some questions or comments or remarks. If someone from the audience, some participant want to ask something.
I can see the question, so I'm gonna start with the last one. Is say, why the Harker variation diagram, there is a lot of scatter in the phosphorus versus silica diagram. The reason of that is because phosphorus is an accessory element in the main composition, so the actual range of variation is less than 1 weight %, controlled by one mineral called apatite. So when you model with major elements, you normally don't consider phosphorus because the variation is because of one particular mineral and very little. You don't consider sodium or even potassium because they tend to be very altered. So you rely on magnesium, titanium, and potassium. Next question, can you say the fault pattern control the direction of the volcano? That's a good one. So she, the person, I don't know if it's a she or a he, sorry, ask if the fault pattern control the direction in which volcanoes occur, or the volcanoes control where the fault control where the volcanoes occur, or the volcanoes control where the fault. So the typical egg and chicken argument. To be more holistic here, I will go even broader and I will say the subduction controls everything. So you get, essentially what you get are two different responses to the bigger tectonic plate control. And then you get volcanism associated with, well, the locus of the melting, which is controlled by subduction. And then you get the fault associated to the same subduction, but in a more tectonic way. So there are two things that are not connected between them, but they have the same cause. And the last question talk about some variation in one of the diagrams. So the task diagram doesn't show variation. I am assuming that you are talking about the Villarrica one. Indeed, the trace element have more variation, and that's to do because at the fine-tuned scale, things are changing. You never get a perfectly homogeneous magma. But the pattern is more or less, well, it's parallel, more or less little variation between the less evolved sample and the more evolved sample. So I will say that I could reproduce those patterns just with a little bit of fractional crystallization without adding the complication of having a different, two different magmas. This is, well, I haven't talked about it, but this has been also corroborated with isotope analysis. So we know that the source of the magmas is the same, and evolution happened later. Sounds good?
Okay, any other question or remark? Okay, so thank you very much again, Professor Cortes, for your presentation and your answers. And as I told to the former speakers, I hope we'll be in contact. And thank you very much again. So before finishing, I would like to thank the three speakers and the panelists, Professor Suppasri, Professor Bielecka, and Professor Cortes, for their participation in this international webinar. They have been very kind and very clear, explaining different aspects about the state of the art and the future perspectives regarding three important topics: about land use, about geological hazards, about the tsunamis, and also about the most scientific and also these signs related with the peligrosity, with the danger, with the hazards of the volcanoes. So thank you very much again, and I hope to see you again. So that's all from my side.
Thank you very much. Un placer.
Un placer.
Thank you for the invitation. Thank you.
Thank you everyone for your time. And
thank you. Thank you.
See you soon.
See you.
Bye.
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 Bye.